Okay, so our podcast going over pages 18 and 19 is going to focus on the electromagnetic radiation and how we do calculations with it. So, jumping right in, we are talking about electromagnetic radiation, which is also known as light. But as you can see from the spectra drawn on your page, light isn't just the visible light that we see by. There's a lot of other types. So a better definition that encompasses all of its permutations is a form of energy that exhibits wave-like behavior as it travels through space. So light is a wave, and that means that it has some properties of our waves that we can compare. So you should probably highlight or emphasize these two kind of lists of facts at either end of this spectra, because you do need to know and be responsible for knowing what types of light have longer wavelengths, which also means they have lower frequency and energy, and then the shorter wavelengths have higher frequency and energy. And so you need to be able to compare not necessarily all of these different types of light, but really focusing on the visible light, because that's the kind of light we're going to be seeing with this flame test that we're doing. So real quick, when we talk about visible light, the colors of light we see, you might recognize as Roy G. Biv: red, orange, yellow, green, blue, violet. But as you can see on my colored copy of this electromagnetic spectrum, those kind of go in reverse order. So I would recommend that you label that visible spectrum there to get the violet on the side that's towards the X-rays and gamma rays, and the red on the side that's towards the microwaves, radio waves, because you might need to know and compare the wavelengths of light or the frequency or energy of this visible light and be able to tell us that red has longer wavelength than blue light. So, hydrogen emission spectrum. This is really what we're going to be focused on, is the flame test and how we can figure out information about the atom using this light. And so a hydrogen emission spectra is the lines of color produced when the electrons in a hydrogen atom are excited. And a couple of words we're going to be using shortly are ground state, excited state, and so I wanted to define those here. Ground state is the lowest energy state of an atom. That means all of its electrons are in those configurations that we've been writing, exactly where they belong. In the excited state, our electrons get some extra energy, some higher potential energy, either from some kind of fire or electricity, and that gets our electrons excited and they jump up to a higher energy level than they should be, which means that our atom has more energy than in its ground state. It has absorbed that energy from the heat or the electricity. So once those electrons jump up into that excited state, they're unstable and they tend to fall back down, and energy is going to be emitted as light, and that allows our electrons to return to the ground state. And when they do that, they're releasing that light, and they're going to make a spectra. And there's two different types of spectra. Continuous spectra is all filled in, all the way from red to purple with every single variation of color in between. There's no gaps. The line spectra that we actually see as the hydrogen emission spectra that Mr. Bohr saw is not continuous. It has separate lines of light here. And one line of red, an orangish, yellowish one, a couple of greens that are slightly different colors, and a blue. But there's big black portions in between, and that's not light that's being released. That's not black light. It's just no light. So there's gaps. There's only specific energies and colors of light being produced. And the reason for this, as we've already kind of talked about in general, comes from the electrons moving between their energy levels, that excited and ground state. So the blanks that you need to fill in here actually kind of sort of line up with this general Bohr model of the atom with all those different energy levels. So we're not trying to fill in all of those lines. That's just to remind you that we have these energy levels in our atom. So each of these lines in our spectra is produced by the emission of photons of certain energies. Those are little packets of light. And the energy of those photons is equal to the difference between the ground and excited states. So here you see this little diagram with the arrows, and that ground state, like we said, is the lowest energy state. The excited state is where they jump to when they get a little bit of energy and they jump up, so that's higher than their normal ground state, but they're unstable. What goes up must come down. So that arrow up shows the absorbed energy, but the arrows down show the amount of energy that's being released. And the only amount of energy that can be released is from that highest excited state to the ground state or one of these other in-between energy levels. But what it can't do is come down 1.5 energy levels. It can't do that because it can't stop there. If it comes down that far, it's going to keep going all the way to the ground state. So as with these arrows, there's only kind of certain starting and stopping points for our electrons, and because our electrons' energies are limited, that meant that the energy of light that we see coming out of our atoms from those electrons is also limited. And let's go ahead and put this into some clearer explanations at the top of the next page. Why do atoms produce unique line spectra instead of continuous? Well, it's because the electrons, which create the light, that's an important thing to know, exist in specific orbits at set energy levels, and they can only move between those energy levels, 1 to 2, 2 to 3, that kind of thing. And because the electrons are only going to absorb and release a certain energy of light, that means they're only going to create certain specific lines of color, not that continuous spectrum. So I know that's a lot, but that's why we kind of introduced that at the beginning, and now we're coming back around to it here at the end after we understand more about our atom in order to kind of revisit this idea. Now, the rest of this page talks about different properties and has some equations on it. The equations are really our focus from here on out. So in this first top chunk, it's this equation, C equals F. Then there's this weird kind of upside down Y symbol. That's the Greek letter lambda, and that represents wavelength. You can see this same equation written out in words. C measures the velocity of our light, F is the frequency, and wavelength is that weird upside down Y. And that equation is actually not so useful in its current form because we're never going to want to calculate C. So it would be a good idea for you to rearrange that equation and write down the two different forms where we're solving for that frequency and wavelength interchangeably there. And then we can make a little side note off in whatever other space you've got left here. This number C is always going to be on your equation sheet. You don't have to memorize it, but we do have to be able to find it and use it when we're calculating these frequencies and wavelengths. So C is 3.00 times 10 to the 8th. Now when you get to class, I'm going to recommend that you do these calculations with my calculator and that you use an E instead of this times 10 to the 8th. You just use E8, and I'll show you how to push those buttons to get it there, but I think it's a lot clearer that that's all one number when you don't have a times 10 in the middle of it. So that just helps us in our calculations there. But you're going to see a few different E's here. And every time you write E, or I write E, if it confuses you, just think of it as times 10 raised to that power that comes after it. So 3 times 10 raised to the 8th power here. But I'll show you how to do that in the calculator, and I think you'll like it. F, like we said, is frequency, and its units are hertz, Hz, which also stands for inverse seconds, or 1/seconds. This tells us how frequently our waves are passing a certain point, so a certain number of waves per second. And then, like we said, that weird upside down Y, the Greek letter lambda, is wavelength, and that always needs to be in meters. There's a chance, though, they might not give you meters. And we'll try not to do this to you ourselves, but the district people always love to throw something at you. So if they give you nanometers, which is a pretty common length for normal visible light wavelengths, then just add E-9 to the end of it to turn it into meters. For example, 350 nanometers is equal to 350 E-9 meters, which technically, if you turn that into proper scientific notation with the decimal after the first digit, would be 3.5 times 10 to the negative 7th, but that is neither here nor there. These are the equations we need to be able to use to find our wavelength and frequency by plugging in our C and whichever of the other numbers that we have. So let's do an example of that. And I know you might not have a calculator that can deal with the scientific notation in these e's that I'm going to use. So for right now, at least, write down these equations with the numbers substituted in, and we can double check that you can push the buttons and get an answer that agrees with mine when you're back in class. So this is asking us to find frequency of green light, which has a wavelength of 4.9 times 10 to the negative 7 meters. So what we need to key in on is our given, that number there, says this is our wavelength, so that's what we're going to plug in as our little upside down y. And it's asking us, our unknown is our frequency. So that's what we want to solve for, and that's what I want an equation for. So if you look back at the equations we wrote down, the one that helps us find frequency, F equals something, is going to come from that original equation, C equals F lambda, of course, but we rearrange it to be F equals C divided by lambda. And if we plug in the C value, 3.00E8, and divide it by that lambda wavelength that they gave us, 4.90 E negative 7, that gets us our answer. And just like always, this crazy long answer coming out of our calculator needs to be rounded to match our givens, which each had 3 sig figs in that base before the E times 10 part. So we're just going to round that to the first 3 digits, 6.12, and then the times 10 to the 14th, of course. And our units for F are hertz. So that's our full final answer. Let's learn about another equation that we can use to do some of these light equations and calculations. Here it talks more about particle behaviors, because this is technically the equation that treats light as a particle, which it can do. What we're really focused in on is that equation, E equals HF. And that is actually going to help us solve for energy, which is that E, if that's what we're asked for. But we also might need to solve for frequency again. And with this equation, F is equal to E divided by H. Now, our E is energy, which will be measured in joules, that crazy J unit that you've seen before occasionally. H is a constant like C. It's just a number. It's always going to be given to you. It's on your formula and equation sheet. Don't have to memorize it. Just find it and use it. 6.63 times 10 to the negative 34, which is what you see it written as right over here. And so I've written mine out with that E in it just instead. And then F is still frequency, which should be measured in hertz. So let's do another problem. This one is asking us for the energy of our wave of light, and it gives us a frequency. Well, if I have frequency and I'm looking for energy, I want an equation for energy that has F in it, and that's sitting right there ready to be used. Just need to take the H value that we have times this F value, and that will get us our answer, which should be rounded to 3 sig figs again. And this energy is measured in joules, so that J just goes right on there. Now, the last problem on your page is a little different, and it might seem like the same as before. It's asking us to calculate energy, but notice here it's giving us our wavelength and asking for energy. And so while E is equal to HF, we can't solve that because we don't have an F. So you could use this green C equation to solve for F and plug that in for F into your E equation. But what I'm going to do real quick is actually plug this equation for F in to the F that's in our red equation there. And what that gets us is H times C divided by wavelength is a way to find energy if I have the wavelength given to me. So this is your third equation, and I would definitely circle this, highlight this. This is going to be your best friend if you're being asked to solve for wavelength or energy when given the other one. Because at this point, H and C are given to you. So we just need to calculate E by taking H times C dividing by that given wavelength, plug it all in carefully in our calculator, and get our answer out, which would be 3 sig figs when rounded correctly, and joules, because that's still energy. So I know these equations look kind of crazy, but they're all given to you. All the constants are given to you. All you need to be able to do is rearrange them to solve for what you need and be able to use the calculator correctly with your scientific notation to get these to turn out right. So we'll work on some of those calculator skills in class together, and I can show you the triangles that'll help you rearrange these equations if you need them. But it shouldn't be as hard as it seems. Even though the numbers seem crazy, the algebra and math part of it is actually pretty straightforward.